Welcome to today's colloquium. It's a pleasure to introduce today's speaker, who I've known for at least a couple decades. I can't remember how long. Qimiao Si is the Harry C. and Olga K. Vice Professor of Physics at Rice University and Director of Rice University's Extreme Quantum Materials Alliance. He obtained his bachelor's degree from USTC in China, and then went to Chicago, University of Chicago, where he did his PhD work. And he's been a postdoc at Rutgers University and the University of Illinois, Urbana-Champaign. Professor Si is a well-known condensed matter theorist, and his major contributions have been on strongly correlated electron systems, including quantum criticality and strange metallicity, high-temperature iron oxide superconductivity, correlated topological matter, and heavy fermion physics. And we're going to hear about some of this work today. He's been the recipient of many awards, including a Sloan Research Fellowship, and he's also received a Humboldt Research Award and was named an Ulam Distinguished Scholar at Los Alamos National Labs. So welcome. Please join me in welcoming Qimiao.
All right. Can I be heard? Very good. So thank you very much, Brad, for the a kind introduction, and also for the invitation, for arranging a beautiful day today. So this talk contains a number of different terms I'm going to introduce. What strong correlations is for folks beyond the condensed matter physics. I'm going to briefly introduce topology, and of course, the heart of the matter is the word phase, phases of matter. By construction, it deals with many-body system, and many-body systems are maybe for good reason has a reputation of being complex, in part because it involves many degrees of freedom. So that's where this colloquium is headed. But I also want to start from something which is very basic. Everybody has dealt with it, the word quantum. And so this is the year of International Year of Quantum Science and Technology. So was proclaimed by UNESCO. And it's good to remind ourselves of some basics. And I'll start from something that sort of the basics in the modern era, in which by certain definition, there's already a quantum computer. So this is one of the IBM machines that has been installed very beautifully, with a beautiful piece of engineering. Looks very striking, at least to me. And it's not the only quantum computer that exists. This is the one that's based on superconducting the Josephson junctions of superconductors, and there are other platforms. It's even being caught up by the beginning stage of the industry. And all this started from some statement that Richard Feynman, or one way of seeing it is that it was a statement by Richard Feynman that saw the seed for quantum computing. In his own way, he said nature isn't classical. So if we want to, I feel like I'm now standing in the right angle. So if you want to simulate nature, you better make it quantum mechanical. And I'm from Rice University, where I saw, in a certain way, the birth of nanoscience and technology. And time will tell whether we are at the stage of quantum computing. That's like what nanoscience and technology stood certain years ago. But if you think about it, and Richard Feynman thought about it, he also said, if you think you understand quantum mechanics, you don't understand quantum mechanics. And I could imagine Feynman meaning a number of different things when he made that statement. So one way to think about, let me figure out where I can stand, and also it connects with the laptop, is that our daily intuition is based on Newtonian mechanics. We learned F equals to ma, and before we learned F equal to ma, if you are age 6, sleeping in the night, having bad dreams about what would happen to yourself if you just jumped a little bit too high in the playground, right? Am I going to come back to the earth? Am I going to come back to my family, to all the love that I have? And then eventually you learn F equals to ma, then you learn that the big earth has attraction for you. So don't worry, you always come back to the earth if you don't do crazy things, right? So what is F equals to ma? F is some gradient of the potential. That's what the Newtonian mechanics makes us to think. It's very important. It keeps us to be where we want to be. Quantum mechanics makes a jump. Instead of treating potential in this way, it treats potential in a different way. And according to Erwin Schrödinger, potential should show up in such an equation that determines a quantity, the wave function. And this wave function is mysterious in a number of different ways. First of all, it tells us that there's a probability distribution as opposed to a deterministic particle that one is dealing with. And this probability, maybe it's this probability distribution that made Schrödinger to be a popular culture figure. So in recognition of the year of the quantum, I was in different parts of Europe and took some pictures. So this is a picture that's on the campus of Vienna University of Technology. In fact, this is the corridor of the building that housed the physics department, maybe. But nonetheless, having Café Schrödinger seems to a reasonable portrait of the recognition that quantum mechanics has retained in the public eye. This is in Zurich. I was giving a seminar in ETH, and my hosts took me to a nice dinner. And after dinner, they said, well, you know, if you are not exhausted, maybe we'll take you to across the street, and there's an interesting house that you might want to see. And this is the house they took me to. It looks big, but otherwise it doesn't look too unusual. But if you zoom in to the corner of this house, you see a cat. And so this is the house, turned out to be the house that Erwin Schrödinger owned when he was in Zurich. And so these are the kind of popular culture features that the statement that we should go from Newtonian mechanics to quantum mechanics evokes. We'll also come to the, instead of just thinking about absolute value of the wave function also deal with the phase, and that we'll come back to that. But this is with this leap. Some of the features, that's a leap from the Newtonian mechanics to quantum mechanics brings us. We also want to think, instead of thinking about pendulum with F equals to ma, we want to think of it as the harmonic oscillator and beyond. And so instead of thinking about F equals to ma, we think about all these quantum states. And so these quantum states, there are lots of them, but imagine that you're allowed to pick only 2 quantum states. There we go. We have the qubit. And so in that sense, why did it take so long to build a quantum computer? Well, it's not all that easy, because if you pick a pair of states to form a qubit, this qubit would be based on some single degree of freedom typically. This qubit would be coupled to a lot of different degrees of freedoms. So noise is a big part of it. Till today, we don't, there's not really error correction method, and it's been coined as a noisy intermediate scale quantum error. And there's also the scalability. IBM machines that I showed you has 100 plus qubits. I think there's a promise that in 3 or 4 years, we'll get to 2,000 qubits based on these Josephson junctions of superconductors. And so it's not obvious that getting to that stage would lead to still being able to have fault-tolerant, have the error correction capacity. So maybe there's room for thinking about alternative platforms, and given that quantum materials deal with many-body system, perhaps there are quantum phases that give you more robust construction for qubits. That could be one possibility, or at least with so many degrees freedom to begin with, so many microscopic degrees freedom to begin with, maybe the scalability is a feature that quantum materials could beat all the existing platforms. This is still to be seen, but it does provide some motivation to think about ways to realize different kinds of quantum phases. Some of you may have heard in the news about the Majorana 1 from Microsoft. It's hard work of the team, gets to the stage. There's still a lot of skepticism about it, but I think the effort should be applauded. And so this provides a motivation to think about quantum phases. So how do we think about quantum phases? If you think about 2-body problem can be exactly solved, 3-body problem cannot be exactly solved, how would we make progress on a system that has many billions of microscopic particles? So it turns out that there are at least 3 ingredients that are extremely important in this pursuit of a variety of quantum phases. One is symmetry. And symmetry was something that was already recognized and taken advantage of from the very beginning of applying quantum mechanics to something like, say, electrons in solids. And so, as we always do in physics, if we deal with a harder problem, let's make drastic approximations to make it as simple as possible to see whether we can have some features that may survive in the final story. So one way to think about the many electrons in a solid, and again, this is like many billions of electrons, that you just ignore completely all the interactions. And so it's a free electron system. And still there are a lot of electrons in it. And that's where symmetry comes into play. the solid, suppose we again make our life simpler by just considering crystalline solid. So you have still a lot of discrete translational symmetry left with the arrangement of the ions. So electrons, and if it's non-interacting, a single electron moving in a periodic potential ends up with the solutions to the Schrödinger equation, the stationary Schrödinger equation that has levels not arranged genetically according to the harmonic oscillators, but arranged in terms of E versus K, where K is a good quantum number that labels the states. And so this feature that condensed matter physicists take for granted and deal with it on a daily basis, the energy dispersion, in fact, one should think of that as very non-trivial feature and a statement that I'll come back to. But for now, just that, I have a K that labels these quantum states. I have other variables to label quantum states as well, different bands, different spin index in the simpler cases. And that's when you see that, when you use that, you're seeing symmetry in action. So that's ingredient number one. Ingredient number two is interactions. And if you think about it, typical electron separation is a scale of electromagnetic scale of a few angstroms. And E squared over R, the Coulomb interaction is, if you think that E squared over Bohr radius is 13.6 electron volts, E squared over several angstroms would be several electron volts. And several electron volts, if you convert into something like a temperature, it's extremely large scale. It's like multiple tens of 1,000 Kelvin. Right? So even room temperature, certainly here, but even room temperature in Houston is a very small scale. Quantum mechanics would be coming into play, and interaction would be coming into play. So symmetry and interactions, this leads to the notion also strong correlations, which I promised to introduce. And all these things turns out to be easier to introduce in insulating settings. So think about now we want to go beyond the simplest of approximations, which is to ignore the interactions completely, but suppose we take into account only the simplest of the interactions, which is the on-site Coulomb repulsion of electrons, and that can only be talked about for single species of electrons between spin up and spin down, and electrons, they're moving around. The dispersion I showed you is not flat, and that can be represented by the quantum mechanical tunneling amplitude. Again, it's the simplest of this. So I'm from Houston, where we deal with traffic on a daily basis. So a good picture, mental picture of electrons moving in a crystalline solid, or in solid at least, is these cars on the highway. And so strong correlation comes in with very drastic consequence. So imagine that we are using the Coulomb interaction U as the tuning parameter for fixed width of band or fixed kinetic energy. When the Coulomb interaction is weak, electrons, the only thing they would avoid doing is that if this site is already occupied by a down electron, this down electron cannot come through it. Pauli principle disallows that. But otherwise, you can think about these configurations and you can convince yourself that electrons can still move around. If I put a battery through this piece of copper, I'm going to drive electricity because electrons are able to move from one place to the other. Now, with this particular count of electrons, one per site of the lattice, and imagine you crank up the Coulomb interaction, at some point you cannot doubly occupy any given site. And so even though in a non-interacting limit we have a metal, the interactions have changed the state of matter. Electrons cannot move around anymore. They act like localized spin, but they cannot move around. If they cannot move around, if I put a certain amount of voltage, I cannot drive a current through the material. It's an insulator. And so that's the Mott insulator. That's a canonical way of localizing electrons and make the electrons to only exhibit spin degrees freedom, something that I'm going to come back to. But for now, this is an illustration of the concept of strong correlations. The Coulomb interactions between the electrons and can change the phase of matter. And so if you implicitly, when I said the things I just said on this page, I'm assuming that electrons are particles. They are charged particles, and there's a Coulomb interaction that acts on it. But it does bring out the important message that we need to keep track of symmetry, but we also need to keep track of interactions. The third ingredient is the phase, which even in the popular culture probably doesn't really get there, at least not really there yet. And so this is a complex, the wave function, it's a complex variable. There's an amplitude and there's a phase. And in all these years of studying quantum mechanics, we've learned that if the quantum state can evolve through adiabatically through the variation of certain parameter, we can accumulate the phase. In solid, this is very easy. We have a lot of electrons, as I said, in the system, precisely because it's a many electron system, and even in a non-interacting case, electrons are forced to occupy different states. Or if you turn around, you can think about states that's following the adiabatic evolution of going from, say, one K variable to another K variable. And so you will have the accumulated Barry phase. And if you have an accumulated Barry phase, certainly you have the possibility of being quantized. And of course, you're in Brown University, and you know what the topology is. But still, experiment like this, when it first came out, seeing the steps, it was fairly astonishing, right? And seeing the steps, the genius of Bob Laughlin is to recognize that these steps are connected with the phase, and all the work that Costas and Thales did all came into this picture of in the popular culture. This probably has made into the popular culture that if you have quantization, it means that there's a robustness. So again, going back to qubits and all that, the need for suppressing noise, etc., sounds like robustness in general is good. And it's a good feature, and we want to take advantage of. And again, these are called quantum Hall insulators. You can see from the longitudinal resistivity and the Hall resistivity, the combination indicates that there's a gap in the electron spectrum in the bulk. And so it's not a real coincidence that insulating systems, as non-trivial as they are somewhat easier to think about in these many electron systems. But the ingredient that this third point brings out is a third ingredient that in affecting the quantum phases in the context we are talking about, namely symmetry, interactions, and topology. So the remainder of the talk is really to play these and there are some other aspects of this, but I'm going to focus on symmetry, interactions, and topology. And in particular, I'm going to focus on the interaction effect, strong correlations, and topology, the phase of the wave function. And I want to make a point which I don't think has been articulated all that clearly, is that it's thinking about the interplay of strong correlation topology, in fact, should be visualized as a two-way avenue for new physics, that strong correlations would enrich topology, leading to new type of electronic topological states, and topology, and this is perhaps less emphasized in the field, is a topology in combination with strong correlations could enable new settings for correlation physics. Now, this slide, in essence, contains half of the condensed matter physics of today, so I'm not going to go through half of the condensed matter physics in this colloquium. I'm going to use two examples, two settings to illustrate this two-way street. And so my objective for the remainder of the talk is to explain these charts, that the strong correlations and correlation physics of strange metallicity can give rise, encoded by a chart like this, and I'll explain that, can give rise to a new form of correlated topology in gapless setting, in metallic settings, and I'll explain what this image means. And conversely, I want to use the example of a recently meaning a year or so old, discovered superconductivity in these transition metal dichalcogenides that the superconductivity reflecting a chart of this, and I want to give my perspective of how to think about it. If you haven't heard the word transition metal dichalcogenides, don't worry too much. When I started working on ion-based superconductors, I was talking to one of my distinguished material science colleague from Rice University, and his quip was that you may have heard about pnictides, but I'm certain that you have not heard the word chalcogenides, and he was more or less right. So I feel like I've come a long way with the materials, the familiarity with the set of materials. So here's a quick outline of some of the things that I want to jump through, and I want to start from the notion that correlations, especially strong correlations, can enable new topological states. I'll start from strong electron correlations, which does not lead to a new topological metallic topological state, but nonetheless endows new features which are by certain metric interesting and important. And then I will combine that with the strange metallicity to talk about a new set of topological semi-metals that are enabled by strong interaction effects and that are not adiabatically connected to the non-interacting limit. So let me start from this. So to explain this, I want to give you two pieces of background for this. One is that we talk about band structure like this, and you can also endow some sign, connect some sign to the band structure, which turns out to be the picture of the topological insulators. And that has generated a lot of excitement over the recent past. But there are cases where symmetry, in particular, could be lattice symmetry, crystalline symmetry, that prevents this gap from being opened up. And in that case, you end up with dispersions like this, where the bands are obliged to cross for symmetry reasons. This looks very innocent, but if you start to think about Barry phase, it turns out that the crossing point is a source of a divergent Barry curvature. And Barry curvature is a term that is very much connected to the Barry phase. And that shows up in experiments, in transport experiment, for example. And since the advent of topological insulators, a topic that's just about 10 years old is the emergence of these what's called Dirac or Weil semimetals. If you are a high energy physicist, or if you want to go into the high energy direction, you may not necessarily be familiar with this band degeneracy, but you know what the Dirac particles are, you know what the Weil particles are. And here's a condensed matter way of generating that. This is the initial discovery work in the angle resolved photoemission experiment that measures dispersions like that and see some crossing of the bands at energy which is not too far away from the Fermi energy. That is either a fortuitous situation, or it was the result of hard work looking for this particular material so that these crossings are happening near the Fermi energy. Generically, it would not. And so the question I want to pose in this part is that if I go from weak correlation, this is a picture of zero interactions, to the strong correlation limit, could there be metallic topological states that are driven by strong correlations in the sense that it's created by strong correlations? If I remove strong correlations effect, it would go away. So this is very much like the quantum Hall insulator I talked about. I showed the steps associated with what's called integer quantum Hall effect, but there are also fractional quantum Hall effect, and that can only be understood if you include interactions. If you switch off interactions, you don't have fractional quantum Hall. So we want to ask the question in the metallic settings, is there analogous affirmative answer that interactions drive topological semimetals? And to do that, I want to also give you a little bit of a general sense. This is like the many-body physics since the 1950s, that if you have all this collection of electrons, suppose it's a metal, what would happen if you go from non-interacting limit, where you can write down exact ground state wave function, a big Slater determinant, and what would happen if you turn on interactions? And so the interaction effects was historically studied by what would be the very natural thing to do in terms of perturbatively treating the effect of interaction. It seems like very natural to think of the reference point. The reference degrees freedoms are bare electrons, and let's ask what would happen if we allow the electrons to interact with each other. It's something that theoretically I can do, controlling model. A number of smart people historically did this analysis, reaching the astonishing conclusion that if you do perturbation theory in interaction to the first order, to the second order, to infinite orders, the system is still adiabatically connected to the non-interacting limit for spatial dimensions higher than 1. And another way of saying the same thing is that this concept of quasi-particles are resilient. A quasi-particle is a particular way of saying that it's an excitation that's adiabatically connected to the bare electron, non-interacting electron. If I project the non-interacting electron into these many-body excitations, there's a quasi-particle associated with a weight z that's less than 1, but is non-zero. So bare electron is something that we can measure by using a photon beam, kick out the electron, and ask for a given wave vector k, what's the distribution of the what's the cross section that you're going to see, and if you see a peak, that peak, by definition, peak as specified by the width being smaller than the energy of the peak energy measured with respect to the Fermi energy. If that's the case, we have a sharp quasi-particle. So you can, so this is the electron spectrum seeing a quasi-particle whose area is less than 1, or you can turn around. Quasi-particle has the expression of a bare electron plus a soup of other things. So whenever you have a quasi-particle, it means that you have resolved the effective interactions in favor of adiabatically being connected to the bare electrons. So that's a central concept. Now, when we want to talk about strong correlations, we want to ask the question, could there be, could this statement of perturbation theory to infinite orders, could that fail? Could we end up with strange metals in which the quasi-particles are lost completely? And so it seems like if you use the electron as a basis, you have to go and do non-perturbative physics. That's a really hard theoretical problem. So whenever there's a hard problem, we do what we learned in all the years of physics textbooks that tell us, just change the basis, and maybe you can make some progress, right? So the basis that we want to change to, and that's why this special class of bulk materials, heavy fermion metals, experimentalists like your colleague Vesla Mitrovic and others work on, has been sort of one of the favorite of the field because it's a canonical example of strong correlations. How so? These systems have multiple species of electrons. Some species of electrons, it turns out that interaction is so strong that effectively they are Mott insulators. That example that I give you. So if the Mott insulators, I already said, they are localized electrons. I don't need to worry about their charge degrees freedoms. I can just think about spin degrees freedom. And then, so in this building blocks, spin becomes part of the building blocks for low energy physics. And I can also have conduction electrons and other things that's part of building blocks. But at least for this species of electrons, there's a physical way of changing the variable, changing the basis that allows one to get away from the perturbative dictation of always ending up with Fermi liquid theory. That's not how historically this subject was dealt with. There's a generation of theoretical condensed matter physicists who worked really hard to use this basis, the spin basis, to recover something that would have been very easy to do, which was to use electron basis to recover Fermi liquid description, to recover quasi-particles. But there's a good reason of using this kind of systems where there's spins and there's a conduction electrons to think about physics that goes beyond the quasi-particle description, and that has been the frontier of this subject over the past decade or two. That's a modern area. The beginning area started in the late 1970s. So qualitatively, how does the change of variable helps? So imagine that I have one species of electrons which are completely localized. So I have a quantum magnetism of these spins, quantum mechanical spins, interacting with each other. This is in the setting called RKKY interactions after Ruderman, Kittel, Kazuya, Yoshida. I think I got the RKKY right. So that's the exchanging that, but you don't really need to know the microscopic symmetry allows this kind of interactions if you choose this variable, and they will be there. And then, so now I've switched to the second quantization, but you really can think of this as the band of electrons that's moving around and not interacting. And if I have a band of electrons that have a spin label to it, I have localized spins. Symmetry dictates that these two species of spins can interact with each other. And it turned out they do, and anti-ferromagnetic, meaning that if it's anti-ferromagnetic, it would favor spin singlet, up, down, minus, down, up. And so up, down, minus, down, up. This up is the spin of the localized moments. That's this big arrow, with creating spin 1 excitations out of spin 1/2 variables. And the spins of the conduction electrons is like removing an electron below the Fermi energy and creating an electron above the Fermi energy. So this is the particle-Hole combination in some spin triplet channel. And what this interaction, called the Kondo interaction, wants to do is to form a bound state of the localized spin and a particle-Hole combination. So it's a three-body, it's a many-body bound state. And I realize I'm invoking Richard Feynman's name a lot. But Feynman also told us that if you know what the ground state is, you can construct excitations. If you know what this ground state is, a bound state like this, you can create excitations by kicking out, just breaking it apart. And if you want to break it apart, you can kick out an electron, that's a bare electron, or you can kick out a composite object like this, which is spin 1, spin 1/2. So it could be either 3/2 or 1/2. I'm going to pick the 1/2 component, and spin is charge neutral, electron or hole is the charge plus or minus E. So this big blob has exactly the same quantum number of a non-interacting electron, spin 1/2, charge E. And that, in essence, is the summary of this generation of theoretical condensed matter physicists creating something called the excitation called Kondo resonance. And this is a quasi... Oops, did I do something? Good. So this is really a roundabout, a very complicated way of getting the quasi-particle back, starting from spin basis, except that it's a very fragile quasi-particle. Z is non-zero, the area is non-zero, but is typically on the order of 10 to minus 3. So if it's already 10 to minus 3, maybe I can bring in some competing interactions to suppress to 0. So that's what the change of variable allows, the possibility. And but before I do that, I want to use this Kondo-generated, the very sluggish particles to do topology. So this is like doing the hard way of Fermi liquid theory, but now I want to utilize the power of symmetry. In this case, a lattice symmetry. I will not get into too detailed. It's actually fascinating diamond lattice, but it has a particular type of symmetry which leads to these band degeneracies, or what we call the topological nodes. And these are wire nodes. But for non-interacting electrons, there's no particular reason that it's located near the Fermi energy, and it doesn't. In a model like this, these are wire nodes sitting far away from the Fermi energy. But once I have the Kondo effect, if I invoke this quasi-particle, which is moving very sluggishly with a weight that's only 10 to minus 3, it also means that this dispersion which I can construct is sitting very close to Fermi energy. In fact, if you have graphene, the bandwidth is typical bandwidth. As I said, typical energy scale is electron volts. This is 3 orders of magnitude smaller. So instead of the usual particle velocity of 10 to the 6 meter per second, these dispersions now have the velocity of the sound of less than 1,000 meter per second. But importantly, the lattice symmetry constraint, which leads to these topological nodes for these many-body generated quasi-particle excitation, it has the same constraint. That's a statement that I can prove mathematically, and it shows up in the calculation. So these nodes are now pinged to the extreme vicinity of the Fermi energy. And that has experimentally observable consequences. One is that entropy, for example, have a particular temperature dependence, which very quickly we worked with experimentalists to confirm it. And the other is that you have these wild nodes sitting very close to the Fermi energy, which is the source of the Berry curvatures. Berry curvature will show up in transporter properties. And it turns out, by certain metric, it leads to 3 orders of magnitude increase of some Berry curvature-induced Hall effect at 0 magnetic field. And that also we worked with experimental collaborators to see. So this is still a Fermi liquid with a twist of topology, but importantly, it amplifies the response. Like the specific heat is T cubed. The prefactor turns out to be amplified by interaction by 9 orders of magnitude. The zero field anomalous Hall effect is amplified by 3 orders of magnitude compared to the expectation. So it makes these things to be much easier to see, and perhaps it's useful. We can also take advantage of symmetry and correlations, interplaying to do material search. I'm not going to go through the procedure, but we actually identify some new materials through this cooperation of symmetry and interaction and with the help of materials database. So that's still a Fermi liquid description, but ends up still with very interesting result of 3 orders of magnitude amplification or 9 orders of magnitude amplification. Now I want to talk very quickly on strange metals and loss of quasi-particles. And so this is actually a recent feature by this journalist, Zach Savitsky, about strange metals. So this is should be considered to be a fairly mundane piece of material, but nonetheless has a strange metal properties. And I'm not going to go into too much details except quoting Savitsky's chart, which is still a bit complicated. So let's not worry too much about the consequence for high temperature superconductivity, potential consequence of saving the world. That's sort of his angle. But think about what is going on. I promised that there's spins and conduction electrons. This change of variable is useful. So what is this? I already mentioned the spin exchange interactions between localized moments. This is the RKKY interaction. I also talked about the antiferromagnetic exchange interaction between localized spins and mobile conduction electrons. That's the Kondo interaction. So there's a tug of war because the spin exchange interactions want to order the spins. It's like a very flat band to begin with. A very natural tendency for these objects is to order. And that's the spin analog of crystals, solid that we see, especially it's expected to be the ground state if you go to very low temperatures. And what the Kondo interaction does from the perspective of the spins is to introduce quantum fluctuations, because if you coupling the spins, localized spins with conduction electrons are moving around and keep on flipping the spin of localized spins. So that induces, that's Heisenberg's uncertainty principle in action. Right? So the Kondo interaction wants to disordering the spin, and the RKKY interactions wants to lead to order the spins, and this is a competition. And the competition can lead to a phase transition between 2 types of ground states. And when we started, it was actually not just out of blue. It was very much guided by experiment. And this is just to give a hint of where we are. I'm not going to go through the whole. This is actually more complicated chart than what I intended to show in the slide. I ran out of time today to prepare the slides, but I did want to make a point that we can actually do calculations to show that due to the tug of war, there is a a loss of quasi-particles, we can look at the many-body spectrum just to show that the quasi-particle description does not work. It's a negative statement, but we can say there are no quasi-particles. Importantly, for the theorists in the audience who think about renormalization group and etc., it's a new fixed point, and it's an interacting fixed point in the sense that KBT is the only scale in the problem. There's no more microscopic scale in the problem associated with this description. And this is important because it means that if I measure dynamics, say sending a neutron beam and ask what's the cross-section when the energy transfer is h bar omega has to scale to be scaling together with KBT, because that's the only energy scale in the problem. And I'm not going to belabel the special functions, digamma functions, except to say that if you go through this quantum critical picture, this tug of war for this critical state, we end up with an understanding of the inelastic neutron scattering data, which had unusual exponent and this scaling to be to actually on a linear scale we can fit it. So this is the this is at least for me it's the most transparent way to see what a digamma function is. It actually fits the scaling curve. It's the analog of black body radiation where you have a particular scaling curve. So this line of work on stranger metallicity is actually, and loss of quasi-particles, is actually grounded in real experiments. This experiment came first, and we thought about how to describe the heavy fermion strange metal to recover, to understand the neutron data. But then we can go on to make predictions. One is the jump of Fermi surface. On one side, you have this blob moving around, which came from spins, but contributing to the electron excitations, quasi-particle excitation. On the other side, it doesn't. And so Fermi surface is a very salient notion. I illustrated in one of the chart, but if you don't know what that is, probably doesn't really matter to know what it is, except that this quantity jumps across a continuous phase transition at zero temperature. So that was a prediction, and that motivated a whole line of experiments that have by now provided very compelling evidence in favor of this jump of Fermi surface. And then you can also ask the question, how could anything jump if it's a continuous phase transition? And that's where the quasi-particle weight, which genetically is 10 to minus 3 for these systems due to strong correlations, if you make these quasi-particle weight to go to 0, then even though it's jumping, but the ground state energy is still continuous. So that leads to a prediction that quasi-particle weight would go to 0, meaning that the quasi-particles would be completely lost. And that statement is also testable, although much harder to test. We used something called thermal transport measurement, but most recently we worked with experimental groups to use noise, what's called short noise, which is the analog of rains coming down to your roof, and you can hear the discreteness. And that turns out to carry the information of a quasi-particle or not. And the experiment provides, so far, the most direct evidence for the loss of quasi-particles. And I want to conclude with this portion by saying that that it turns out that there's some entanglement quantity which in the condensed matter community, which don't really normally deal with it. But if you are open to dealing with it, it turns out that it gives a picture for the spins which are entangled with each other, preventing them from entangling with the conduction electrons, and that turns out to be a positive characterization of the loss of quasi-particles. And this quantum Fisher information is something that recently has been measured. We can compare what do we calculate theoretically with experiment to show that indeed that's consistent. So this is the chart. This explains the chart T-linear resistivity, I didn't actually get into. That's a defining feature of strange metals. But my point is that it's accompanied by this dynamical h bar omega over kBT scaling, loss of quasi-particles, Fermi surface reconstruction, and something that I didn't talk about, enhancement of physical entropy. That's the emerging profile of the strange metal. So what we have done more recently is to combine this Fermi liquid with the twist, strongly correlated, but still Fermi liquid with the twist, and the loss of quasi-particles to get these topological semi-metals that do not have quasi-particles. And am I coming to more or less the end of the time, or a couple of minutes? Yeah. So let me try to jump through. So the point is that a plot like this turns out, maybe it doesn't look drastically different from this, but turns out to be drastically different from this in the sense that here the width of the peak is smaller than the energy. The peak energy measured from Fermi energy, here it's not. It's a very broad peak. And so that's not describing by a quasi-particle, but it turns out this is showing microscopic calculational result, but it turns out that we can also make a symmetry-based statement that for example, these two broad peaks must come together at some special K, symmetry-dictated K, where they're on top of each other. So the spectral crossing replaces the band crossing as the telltale sign of the topological nodes. And we can calculate physical responses that capture the topology. We can look at the surface states that also is dictated by bulk boundary correspondence, except none of these is a quasi-particle. They are all extremely broad. And more recently, we worked with an experimental colleague from Vienna to identify this material, this particular heavy fermion material where it's the closest to what I talked about strange metal, which is a tug of war between these two types of competing interactions. And so again, you have two broad peaks for giving K versus energy that have to come together at some special K. So this color plot is like is representing the same thing here, except that now I have to look at it vertically. For giving K, I have to look at a spectral function and see that there are two peaks. And at that point is where the symmetry dictates that they must merge. And so this is a version of topological semi-metals, the topological node, but without quasi-particles. And this topological phase has, again, all the features of extreme responses in transport and in thermodynamics that captures strong interacting nature, except that theoretically it cannot be adiabatically connected to a non-interacting case. And experimentally, as it turned out, these features show up as a dome, very much like high-temperature superconductor in the phase diagram of the high-temperature superconductors shows up as a dome in the vicinity of quantum critical points. So maybe in 1 minute, let me describe the second direction, which is that instead of asking interactions to generate a new type of topology, can we use topology to generate new correlation physics? And this is done in this transition metal dichalcogenides case with the twisting, the moiré structure. And for the condensed matter folks in the audience, probably you've seen this sort of electronic states in the presence of twisting or in the moiré structures. And let me just make a statement that experiment discovering the superconductivity came as a surprise, but attached with that surprising discovery is a number of features which connects very much to what we see in bulk materials like heavy fermions, cuprates, etc. Namely, it's commensurate. The filling is 1, so it's like a Mott insulator is part of a story. And there are all the indications for interaction being strong. There are all the indications that the system is sitting at the boundary between the two competing forces. It's a high temperature superconductivity if you talk about dimensionless temperature. And so I think I only want to make really one conceptual point, namely when you do twisting, make these artificial engineered structures, the goal was to make the bands really narrow. Like instead of 1 electron volt or several electron volts of energy dispersion, you make the energy dispersion of several milli-electron volts. And if you have a half-filled band, there's a long-standing condensed matter notion that you should order. Mott insulator is a good example of the other examples. And in this material, there is order. These are these red blobs. But superconductivity happens by suppressing the order. So what's the driving force for suppressing the order? That requires quantum fluctuations. And it turns out that these bands are topological, as labeled by the Chern numbers of a particular valley. That's a detail, but these are topological bands. And topological bands, usually you would think just half-filled flat band, and you go to real space, you solve the interacting problem. Except that the Berry phase, the topology, does not allow you to go to real space. There's some singularity in the phase. And one way to resolve that is to combine this flat bands with nearby bands, so the total topological index adds up to 0. But when you do that, you have to do some canonical transformation to change basis yet again to make effectively